Hello everyone. Today I'm going to be talking about the greedy method, an algorithm for learning under test and budget. It's a joint work by me and my advisor Keenan Weinberger and Oliver Chapeau. So in the past few years, machine learning algorithms have successfully entered into industry through many real-world applications, such as web search ranking, email spam filtering, and product recommendations. So the industry is slightly different from academia. In academia, when we design an algorithm, we want to maximize the accuracy, and the testing cost is not that important because usually algorithms are executed only once, so the testing cost is usually low. Whereas in industry, when we design the algorithm, we still want to maximize the accuracy, but now the testing cost is really high because a lot of algorithms are executed millions of times every day, so we have to make sure our algorithm can satisfy the hard test time CPU cost constraints. So let's introduce a new setting. So in traditional machine learning setting, we have the training set, and we want to learn a classifier HX that maximize the accuracy. Whereas in the new setting, we have to consider the test and budget. We want to learn a classifier not only maximizing the accuracy, but also satisfy the budget during the test time. So in this work, we focus our classifier HX on stage-wise regression or gradient boosting. So our classifier HX is an additive classifier, iteratively adding weak learners to our classifier. And usually these weak learners are regression trees. And we build out these trees by minimizing loss function. The loss function can be a square loss for regression problem or logistic regression loss for classification problems. And at each iteration, we generate a new tree. That minimizes the loss function. And the new tree is limited depth regression tree generated by CART algorithm. And we add this new tree to our classifier HX. So having introduced our classifier HX, now we can take a close look at the test time cost. The test time cost contains two parts. The first part is tree evaluation cost. The other one is feature extraction cost. The tree evaluation cost is the cost of transforming your feature representation to the weak learner prediction HX. And because our weak learners are limited depth regression trees, they share the same depths, so the tree evaluation cost is constant among all the trees. So for example, if we have T trees, the total tree evaluation cost is a T times the constant CE. And the feature extraction cost is the cost transforming your raw input feature into feature representation X. Because once we extract a feature for the first weak learner, we don't have to extract the feature again, the same feature again for the later weak learners. So we define a used feature set fh to indicate what feature we have already extracted, we've already paid for, so we don't need to extract them again. For example, the first weak learner, we have the first split is on the red feature, and we include the red feature into our feature extraction cost. The second one is the same, is also red feature. We don't have to include it again. So the only new feature is the white feature. And same for the second tree, because the red and white feature are already extracted, we have already paid for, so the only new feature is the yellow feature. The same thing to the last tree, the only new feature is the blue feature. And so the total feature extraction cost is the sum of all the feature costs in the used feature set. So this is the test time cost. To reduce the test time cost, people have already come up with a lot of ideas. A group of them is called early exit. So they build out this. So the idea is build out these trees without considering the test time cost, and then they set the threshold and do early exit. And to early exit a lot of data points, because most of the data points are early exited by those thresholds, only a few of them can go through all the weak learners. So the amortized test time cost is reduced. But you can see the problem, because when they build out these trees, they don't consider the test time cost. It's very likely that the very first few trees use a lot of expensive features. So to overcome this problem, people come up with post-process algorithms. Same to the early exit, what they do is still build all these trees without consider test time cost, but then the reorder will reweight all these trees to minimize the test time cost. And then they set the threshold and early exit. Now, because the first few trees, the first few trees mostly use cheap features, the MR test cost is greatly reduced. So our algorithm we refer to as the greedy miser, which is totally different from all this previous approach. We consider the test time cost from the very beginning, and we carefully generate all these trees with the test time cost in mind. So we don't blind out. We generate these trees with the test time cost in mind. So how do we do this? We form it into a optimization problem. The objective is to minimize the loss, and such that the tree evaluation cost is less than tree evaluation budget, and feature extraction cost is less than feature extraction budget. And because, as you see, the tree evaluation cost is the number of trees times a constant, so it is bounded by the maximum number of trees and iterations. So we can easily remove it from the constraint. And also we can use Lagrange formulation to move the feature extraction cost from constraint to objective. And the Lagrange multiplier is exactly the trade-off parameter for feature extraction cost and accuracy. And then at each iteration, we minimize this loss function. So we want to find a new tree that not only minimizes the loss, but also minimizes the cost, feature extraction cost introduced by this new tree. And we solve this using modified card algorithm. So a high-level picture, the regular card algorithm find a direction or a tree that is the steepest descent to the original loss, whereas our modified card algorithm find the direction that is best trades off the cost and descent. So it's just a high-level picture. Details in the full paper and posters. So let's come to the result. We first test our algorithm on the Yahoo Learning to Rank dataset. So the dataset contains query and result pairs. The labels are from 0 to 4. 0 means the resulting web page is totally irrelevant to the query. 4 means the resulting web page is a perfect match to the query. And features are keywords, number of hits, and etc. The feature cost is basically the extraction time for that feature. And we obtain all this feature extraction time from Yahoo ranking experts. And this figure shows the accuracy and cost performance. The y-axis is NDCGF5, which is a popular ranking criteria. The higher, the better. The x-axis is the budget. So our goal is to find a classifier or design a classifier that can achieve really high NDCG5 score with very low budget. And the first baseline is the stage-based regression. So it doesn't consider any custom cost. So although it has a really high NDCG5 score, it uses all the features and all the trees, so it's really expensive. The second baseline is a naive extension to stage-based regression. We basically group all the features by their feature cost, and then gradually incorporate more expensive feature groups. So as beginning, we only incorporate features that have feature cost less than 5 and less than 50, 55, 150, and finally all features. And although it reduces the cost, but it also hurts the NDCG5 score quite a bit. And we also compare against the early exit and Cronus, which is a post-process algorithm from our group. And we generate the curve of our greedy miser by changing the feature extraction cost and accuracy trade-off parameter lambda. And as you can see, when the greedy miser maintains really high score even when the budget is almost 1/10 of the total cost. So why does the greedy miser work really well? Well, we analyze the feature extracted by the greedy miser, and we group out feature by their feature cost, and the numbers in parentheses indicate how many features in that group. And the y-axis is the fraction of used features. Like 0.4 means 40% of the feature are used by the greedy miser, and the x-axis is the budget. So in general, when we lower the budget, Greeniemizer use fewer features. But you can see for cheap features like this one, which is the feature cost 1, Greeniemizer use pretty much the same amount of features in all budget settings. Whereas for the more expensive features, the Greeniemizer dramatically decrease the usage as we lower the budget. It's interesting to point out that the Greeniemizer uses the most expensive features, like feature cost 200, across all different budget settings. So although the feature is really expensive, but it's also is very useful, this may explain why Greeniemizer can achieve really high accuracy at very low budget, because it can cherry pick some really useful but expensive features at the beginning. All right, and they also test on a totally different scenario. They test on scene 15 dataset. So the dataset contains a lot of images, and the goal is to classify the scene of each image. So in total, the dataset contains 15 different classes, 15 different scenes, including bedroom, coast, street, or something. The features are a variety of vision features, including densive, hog, SSM, etc. The feature extraction cost is basically the running time for those vision algorithms. And here's the cost and accuracy performance. As you can see, the y-axis is the budget, is the accuracy. The higher, the better. The x-axis is the budget. And same as before, stage-wise regression, which is a cost-insensitive algorithm. So although it's really high in accuracy, but it's really expensive as it extract all the features and trees. And early exit, although it improves the cost, it reduces the cost, but also it hurts the accuracy quite a bit. SVM multiple kernel is similar to stage regression, although it achieves really high accuracy, but it's really expensive because it uses all the features. And Greeniemizer, our algorithms achieve relatively high accuracy when the budget is 1/5 of the total cost. In conclusion, we designed a new algorithm, which is Greeniemizer. It incorporates the cost at when building each tree is different from previous approach, and it matches the accuracy at lower cost. And it has two intuitive meta parameters. The total number of iterations controls the tree evaluation cost. The Lagrange multiplier lambda trade-offs the feature extraction cost and accuracy. It handles both regression and multi-classification problem, and because it's a variant to the card algorithm, so it naturally scales to very large data set. Okay, that's it. Thank you. Any more questions, you can always go to the poster session. Thank you.